Every year, thousands of quarries crush millions of tons of rock. The biggest dragline in history, Big Muskie, weighed 13,500 tons. That's like 10,000 cars. But the real star isn't the machine itself, it's the teeth. Parts weighing up to 150 pounds that bite into granite every single day. How does ordinary steel transform into nearly impenetrable armor? Today you'll see the complete cycle, from molten metal to a tooth that survives 50,000 impacts. If you want to see how they make the fangs of giants, subscribe to the channel. Here we show you the operations that tear into the earth. Big Muskie weighed 29,779,800 pounds. The bucket could fit 2 buses side by side. Bucket capacity, 4,300 cubic feet. 60 teeth on the bucket. Each tooth weighs 50 to 150 pounds. A tooth isn't just a chunk of iron, it's an engineering marvel that bites into granite day after day without wearing down. Teeth are made using 2 methods, casting and forging. Right now, you're seeing casting. Material: alloy steel with nickel and molybdenum. Molybdenum improves hardening, nickel provides toughness and corrosion resistance. Carbon content from 0.33 to 0.5%. That's high carbon steel. It's hard after quenching. Steel melts in an electric arc furnace. Temperature: 2,692 degrees Fahrenheit. 3 graphite electrodes. Arc between electrodes and metal. Power: 10 megawatts. Furnace holds 20 tons. Melting time: 2 hours. Steel gets purified. Sulfur removed with lime. Phosphorus by oxidation. Then the metal stirred in an argon-oxygen deoxidizer. Argon blown in from below. Pressure: 73 psi. Flow rate: 79 gallons per minute. Argon bubbles rise. Mix the melt. Carry gases to the surface. Hydrogen content drops from 10 to 2 parts per million. Oxygen from 80 to 20. Low gas content is critical. Gas bubbles become cracks. Finished steel pours into a ladle. Ladle lined with refractory. Melt temperature: 2,649 degrees Fahrenheit. Ladle holds 2,000 pounds, enough for 20 to 30 teeth. Investment casting. First, they make a wax model. Wax melts at 158 degrees Fahrenheit. Pour it into the die. Cool it down. You get a wax copy of the tooth. Accuracy down to a few thousandths of an inch. Models are assembled onto a sprue tree, 5 to 10 teeth per tree. The tree gets dipped in ceramic slurry. The slurry is fine zirconium powder in colloidal silica. Particle size about 2/10,000ths of an inch. Dip the tree. Pull it out. Coat with coarse zirconium sand. Grit size about 1/100th of an inch. Dry it. Repeat 7 to 10 times. Each layer about 1/16th inch thick. Final shell thickness roughly ½ an inch. The shell withstands 2,800 degrees Fahrenheit. That's the steel pouring temperature. They melt out the wax. Heat the mold to 1,500 degrees. Wax melts, flows out through openings, leaves behind a cavity that's the exact shape of the tooth. Pouring. The mold heats up to 1,800 degrees Fahrenheit. A hot mold means less thermal shock during the pour. A crane brings the steel ladle into position. The steel's at 2,650 degrees. It glows bright orange. They pour fast but carefully. Pour rate is 4 pounds per second. Air bubbles will kill the part. Metal fills the mold from bottom to top. Pushes air out through the top. After pouring, they don't touch the mold. Cooling is slow, 8 to 12 hours to reach room temperature. Fast cooling means cracks. Slow means proper structure. Once it cools down, they break the shell. Sandblasting machine. Pressure at 120 psi. The sand is corundum, grit size 20 micrometers. The ceramic cracks and crumbles away. Underneath, a gray cast tooth. Surface is rough, ceramic remnants in the recesses, but the form is precise. Deviation from the blueprint is less than a millimeter. Heat treatment. First stage, normalizing. The teeth get loaded into the furnace. Temperature, 1920 to 2070 degrees Fahrenheit. Hold time, 10 hours. At this temperature, the steel recrystallizes. Large grains break down into smaller ones. The structure becomes uniform. It's like muscle recovery after a workout. The metal gets stronger and more flexible. Air cooling. Cooling rate, 90 degrees per hour. Second stage, hardening. Heat to 1870 degrees. Hold time, 2 hours. Then rapid cooling in oil. Oil temperature, 140 degrees. Cooling rate, 540 degrees per second. The structure transforms into martensite. That's a needle-like crystal lattice, extremely hard. Hardness after quenching, 59 to 63 on the Rockwell C scale. That's harder than a file. But hardened steel is brittle as glass. One strike, crack. That's why there's a third stage, tempering. Heat to 400 to 500 degrees Fahrenheit. Hold for 4 hours. This relieves internal stresses, adds flexibility. Hardness drops to 48 to 52 units. Perfect balance. Hard enough not to wear down, flexible enough not to break. Some manufacturers use induction hardening. The tooth gets placed in an inductor. Current frequency 400 kHz. Power 100 kilowatts. The surface heats up in 3 seconds to 2700 degrees Fahrenheit. Heating depth 0.04 to 0.08 inches. Immediately cooled with water. Pressure 145 pounds per square inch. Flow rate 26 gallons per minute. The surface hardens. The core stays soft. Surface hardness 58 to 63 units. Hardened layer depth 0.05 inches. Quality control. Every tooth gets checked with ultrasound. The probe generates waves at 5 MHz. Waves pass through the metal, bounce back off defects. A crack just 0.2 inches wide? Rejected. They check hardness with a Rockwell tester. A diamond cone presses down with 330 pounds of force. They measure the depth of the indent. Below 48 or above 52? Rejected. Too soft, it'll wear out fast. Too hard, it'll crack. The teeth get ground down. Grinding wheel made of aluminum oxide. 80 grit. Speed of 67 miles per hour. Takes off the rough spots from casting. Surface roughness drops from 0.001 inches to 0.00012 inches. Smooth surface holds up better against wear. Rough spots wear down faster. Marking. Every tooth gets a number. Laser engraving. Laser power 50 watts. Engraving depth 0.004 inches. The number shows the batch, date, and specs. Testing. One tooth from the batch gets sent to destruction. A hydraulic hammer strikes with a force of 1,000 pounds. Impact every 2 seconds. They count cycles until failure. A quality tooth withstands 50,000 strikes. Wear test. The tooth gets abraded. Quartz sand with 500 micrometer grain size. 5 bar pressure. 100 hours. That's equivalent to 1,000 hours of operation. The best teeth lose less than 0.5% of their weight. Production numbers. A big dragline, bucket holds 4,300 cubic feet, 60 teeth on the bucket. Each weighs 66 to 150 pounds. Teeth get replaced every 3 to 6 months. One dragline wears through 80 to 120 teeth per year. Hundreds of draglines operate worldwide. 50 large machines in U.S. coal mines alone. Tens of thousands of teeth produced annually. One tooth costs $1,000 to $3,000. 60 teeth per bucket, $180,000 just for consumables. Replace twice a year. That's why every tooth must be perfect. The economics of mining depend on the reliability of these steel fangs. That's how dragline teeth are made. From molten steel to a part that chews through granite. If this was interesting, hit that like button. Write which quarries you've seen. Subscribe. We show how giants are made.
What if I told you there's a metal that's 15 times rarer on Earth than gold? And to mine just 1 ounce of it, you need to process 10 tons of ore. A metal whose entire annual supply would fit in an ordinary room, while all the gold in the world would fill 3 Olympic-sized swimming pools? Every year the world produces only 180 tons of platinum. That's 17 times less than gold. South Africa produces 120 tons, 74% of global production. Russia's in second place with 23 tons. To extract 1 ounce of platinum requires processing 10 tons of ore, while for gold, just 2 to 3 tons. The Merensky Reef, Upper Group 2, and Platreef contain only 2 to 10 grams of platinum per ton of ore. After flotation, the concentrate is heated to 1500 degrees Celsius to burn off iron and sulfur impurities. Then they use aqua regia, a mixture of nitric and hydrochloric acids, to dissolve the platinum. The concentration of platinum in Earth's crust is only 0.5 parts per million. Stick around till the end. You'll discover a secret that even jewelers won't tell you. Picture an underground mine several miles deep somewhere in South Africa, in the Bushveld province, home to the world's largest platinum deposits. These aren't open-pit mines. They're narrow tunnels blasted through rock up to 2 miles beneath the surface. Here, platinum is extracted from thin layers, reefs, that stretch for hundreds of miles but measure just 6 inches to 5 feet thick. 3 main reefs: the Merensky Reef, Upper Group 2, and Platreef. The Merensky Reef, discovered by Hans Merensky in 1924, has historically dominated global platinum production. Here, platinum reaches its highest concentration, 50 to 60% platinum group metals. Upper Group 2, a chromite-rich reef, more stable but with lower gold, copper, and nickel content. Platreef, a wider reef with lower platinum grades but higher base metal content, roughly 5 times more. Miners drill holes into the reef walls and pack them with explosives. After detonation, the shattered rock containing platinum and other metals is transported to the surface for processing. The ore gets crushed, then goes through flotation. That's a process that separates minerals based on how they stick to air bubbles in water. Mills grind the ore down until 60% of the particles pass through 75 micrometers. Then the ground ore gets mixed with water, and collector reagents are added, things like xanthates and dithiophosphates, which make the sulfide minerals containing platinum hydrophobic. Water repelling. Air gets pumped through the mixture, creating millions of tiny bubbles. The hydrophobic particles containing platinum stick to the bubbles and rise to the surface, forming a froth that gets skimmed off. Hydrophilic waste rock particles stay at the bottom. Platinum in Merensky ores is closely tied to base metal sulfide minerals: copper, nickel, and cobalt. The platinum group metals are present either as discrete platinum group minerals included in or attached to the sulfides, or in solid solution with the sulfides. The base metal sulfide minerals in Merensky: pyrrhotite, pentlandite, chalcopyrite, and traces of pyrite. After flotation, the concentrate still contains less than 1% platinum. Now, the concentrate heads to the smelter. It's dried and then heated in electric furnaces to temperatures exceeding 2700 degrees Fahrenheit. Air is blown through the molten metal to oxidize iron and sulfur impurities. Sulfur oxidizes to sulfur dioxide and gets removed as exhaust gas. Iron oxide is removed as phyllite slag. Platinum's melting temperatures are significantly higher than other metals due to the presence of chromium, which makes them incompatible and requires special furnace design. The power capacity of platinum smelting furnaces reaches 19.5 megavolt amperes and 68 megavolt amperes. Energy consumption runs 800 to 850 kilowatt hours per ton of concentrate. Platinum's high melting point means impurities like iron burn off, and the result is a powdery sludge of platinum group metals: rhodium, iridium, ruthenium, and osmium, plus platinum itself. The converter's slag phase contains significant amounts of trapped platinum metals and gets recycled back to the smelting furnace to recover those captured metals. The converter mat gets cooled down, crushed, and processed at a base metals refinery. Here, hydrometallurgical processes dissolve the copper and nickel, leaving behind a residue rich in platinum group metals. This platinum metals residue heads to a precious metals refinery, where various solvent extraction and precipitation methods separate out the individual metals. Getting pure platinum requires further refining. Typically, this involves aqua regia, a mix of nitric and hydrochloric acids in a 1:3 ratio. Aqua regia is one of the few acids that can dissolve platinum. When the concentrate is treated with aqua regia, the acid produces chlorine, which bonds with the platinum, forming chloroplatinic acid. The final step uses ammonium chloride to convert the chloroplatinic acid into ammonium hexachloroplatinate, which can be calcined to yield pure metallic platinum. Platinum content in the residue after hydrometallurgical processing can reach 5,900 ounces per ton. That's an enrichment of nearly 500 times compared to the original flotation concentrate. Now, a bit of history. In 1735, Antonio de Ulloa and Jorge Juan y Santacilia witnessed indigenous Americans mining platinum while the Spanish traveled through Colombia and Peru for 8 years. Ulloa and Juan found mines with whitish metallic nuggets and brought them back home to Spain. Antonio de Ulloa returned to Spain and established the first mineralogical laboratory in Spain and was the first to systematically study platinum, which happened in 1748. In 1783, French chemist François Chaboneau was the first to obtain a pure sample of platinum metal. In 1801, English scientist William Wollaston invented a method for efficiently extracting the metal from ore. Growing demand for the metal led to the discovery of major deposits in the Ural Mountains in 1824 and in Canada in 1888. This ultimately led to geologist Hans Merensky's discovery of the largest platinum deposit on Earth in 1924. Platinum is primarily used in automotive catalytic converters. In 2014, out of 218 tons of platinum sold, 98 tons, 45%, went to vehicle emission control devices. 74.7 tons, 34%, to jewelry. 20 tons, 9.2%, to chemical production and petroleum refining. 5.85 tons, 2.7%, to electrical applications like hard disk drives. The remaining 28.9 tons went to various other minor applications, such as medicine and biomedicine, glass-making equipment, investments, electrodes, anti-cancer drugs, oxygen sensors, spark plugs, and turbine engines. The most common use of platinum is as a catalyst in chemical reactions, often in the form of platinum black. It's been used as a catalyst since the early 19th century, when platinum powder was used to catalyze the ignition of hydrogen. In automotive catalytic converters, it completes the combustion of low concentrations of unburned hydrocarbons from exhaust gases into carbon dioxide and water vapor. Platinum is extremely rare on Earth, occurring at a concentration of just 0.05% in the Earth's crust. Platinum often occurs chemically unbonded as native platinum and primarily as an alloy with other platinum group metals. Most commonly, native platinum is found in secondary deposits among alluvial sediments. The alluvial deposits used by pre-Columbian peoples in the Chaco Department, Colombia, are still a source of platinum group metals today. Another major alluvial deposit is located in the Ural Mountains, Russia, and it's still being mined. When comparing the rarest precious metals by annual mine production, platinum is far rarer than gold. We're talking about more than 15 times rarer by annual output. In 2018, silver, gold, and platinum mine production totaled 860 million ounces, 108 million ounces, and 6 million ounces respectively. Producing a single ounce of platinum requires about 10 tons of ore. For comparison, gold needs around 2 to 3 tons of ore to produce 1 ounce, while silver takes 5 to 10 tons per ounce. Global demand for platinum in 2023 was estimated at 7.5 million ounces. The world's largest platinum producer, Anglo-American Platinum, produced 1.75 million ounces of platinum in 2023. Russian company Norilsk Nickel produced 593,000 ounces of platinum in 2022. Every year, an additional 2 million ounces, 60 tons of platinum, comes primarily from recycling auto catalysts and jewelry. What makes platinum stand out is just how difficult it is to extract. Platinum mining is extremely labor-intensive. The KEL process represents a potentially significant improvement in platinum concentrate processing technology from an economic standpoint through dramatically reduced energy costs. Compared to matte smelting, electricity consumption drops by 82%, and overall carbon dioxide emissions decrease by 70%. And so, having traveled from a thin reef deep underground in South Africa, through blasting, crushing, flotation with millions of bubbles, through smelting at 1500 degrees Celsius, through dissolution in aqua regia, through precipitation with ammonium chloride and calcination, platinum is born. A metal 15 times rarer on Earth than gold, requiring 10 tons of ore to be processed for a single ounce, whose entire annual supply, just 180 tons, would fit in a single room. A metal that catalyzes chemical reactions, cleans the exhaust of millions of cars, and adorns fingers with jewelry that never corrodes. "60 days. That's exactly how long it takes for an empty Coke can to become a brand new can on a store shelf. You finish your drink, toss the can in the trash, and 2 months later that same can is back in the supermarket. But this isn't magic. It's aluminum recycling, the most profitable recycling process on the planet. Every recycled can saves 95% of the energy compared to making new aluminum. It's like the difference between taking a walk and flying to another continent. Every year, 600 billion aluminum cans get recycled worldwide. Weight, 20 million tons. Value, $50 billion. And here's the most amazing part. Aluminum can be recycled infinitely, without losing quality. Metal that's been melted down 1,000 times is identical to fresh aluminum. How is that possible? How does a dirty crushed can turn into a perfectly clean sheet of metal? Stick around till the end. You'll see the most perfect closed-loop system ever created by humans. Every second, 20,000 aluminum cans get tossed worldwide. In a minute, over 1 million. In a day, 1.5 billion. That's a mountain of metal as tall as Everest, and all of it needs collecting, sorting, recycling. The process starts on city streets. Blue-marked trash bins went for recyclables. Trucks gather the contents and haul them to sorting facilities. Conveyor belts here stretch over 300 feet. Everything moves down the line: cans, bottles, cardboard, plastic. The job? separate aluminum from everything else. And this is where technology kicks in. Powerful electromagnets hang above the conveyor. But aluminum isn't magnetic. So how do you pull it out? The magnets create eddy currents. A rapidly changing magnetic field induces a current in the aluminum, and that current creates its own field. This field repels the cans away from the conveyor. They literally jump up and fly into a separate bin. One separator processes 15 tons of trash per hour. Pure aluminum drops into the collector. Everything else keeps moving down the line. Next up, cleaning and prep. Cans arrive dirty. Beverage residue, labels, paint. All of it's gotta go. Cans get loaded into massive drums. 10 feet across, 30 feet long. Inside, water and alkaline solution. The drum spins. Cans scrub against each other. Dirt, labels, paint wash away. Water drains through filters, leaves nothing but clean metal. Then drying. Hot air at 300 degrees. Fahrenheit evaporates moisture in 15 minutes. Now the cans need compressing. A hydraulic press generates 300 tons of pressure. 1,000 cans become a dense block weighing 45 pounds. These blocks are called bales, easy to store and transport. A truck can haul 15 tons of bales. That's 750,000 cans. Bales get stacked in open yards. Aluminum doesn't rust, rain can't hurt it. It waits its turn for remelting. Some blocks sit a week, others a month. But they all end up in the same place eventually, the melting furnace. (1827). German chemist Friedrich Wöhler produces pure aluminum for the first time. Tiny beads of silvery metal. Light as wood, but strong as iron. Beautiful as silver, but it doesn't tarnish. The world goes crazy. Aluminum gets called the metal of kings. Its price, $1,200 per kilogram. That's 3 times more expensive than gold. French Emperor Napoleon III orders aluminum silverware for his most important guests. Everyone else eats with gold, it's cheaper. The problem is, aluminum is incredibly hard to extract. It's hidden in ore, bauxite. Extracting it chemically is nearly impossible. You need tons of reagents and weeks of work for a single gram of metal. Things change in 1886. American Charles Hall and Frenchman Paul Héroult independently invent the electrolytic process. You run current through molten ore. You get pure aluminum. Simple, fast, cheap. The price drops from $1,000 to $2 in 20 years. The aluminum revolution begins. The 20th century turned aluminum into the planet's most widely used non-ferrous metal. Airplanes, cars, electrical wiring, beverage cans, aluminum everywhere. By the 70s, global production hits 10 million tons a year. But there's a problem. Producing aluminum from ore demands monstrous amounts of energy. To get 1 ton of metal, you need 15,000 kilowatt hours of electricity. That's a year's worth of power for the average American home. Plus carbon dioxide emissions, landscape destruction from open pit mines. Environmentalists sound the alarm. Then someone grasps the obvious. Aluminum doesn't degrade. A can tossed in the forest will sit there 200 years unchanged. But what if you melt it down? Energy cost? Just 700 kilowatt hours per ton. 20 times the savings. No need to mine ore, no need for chemical reagents, no need for giant electrolyzers. Just melt the metal and use it again. The recycling era begins. In the US during the 70s, 15% of cans got recycled. Now, 50%. In Brazil, 98%. That's the highest recycling rate of any material. The smelting shop. Air temperature near the ceiling, 122 degrees Fahrenheit. In the center of the hall stands a furnace as tall as a 3-story building. They call it a reverberatory furnace. Inside, a bath of molten aluminum. Temperature, 1400 degrees Fahrenheit. The metal glows orange. Heat dances above it. Briquettes feed in by conveyor straight into the furnace. The aluminum melts instantly, melting point. Just 1220 degrees. That's 2.5 times less than steel. The energy savings are massive, but trash floats in the melt. Paint residue, varnish, impurities from other metals. They need to be removed. Chlorine gets blown into the bath. The gas rises in bubbles through the melt. It binds the impurities and carries them to the surface. Dross forms, gray foam. It's scraped off with mechanical rakes. Beneath the dross, a mirror of pure metal. After 6 hours of melting, the furnace is ready to tap. A massive ladle rolls in from below. The furnace tilts and the melt pours out in a golden stream. One ladle holds 20 tons. That's 1 million cans in liquid form. The molten metal gets poured from the ladle into molds. Out come ingots weighing 25 tons each. Length, 33 feet. Width, 5 feet. Thickness, 20 inches. They cool for 24 hours. Temperature drops from 1300 degrees Fahrenheit to room temperature. The ingot solidifies but stays soft and pliable. That's aluminum for you. It deforms easily. Next stage, rolling. The ingot heads to the rolling mill. This giant machine has rollers 6.5 feet across. The ingot passes between the rollers. Pressure, 1,000 tons. The metal flattens like dough. In one pass, thickness shrinks from 20 inches to 8. The ingot passes through the rollers again. Now it's 4 inches thick. Another pass, 2 inches. Another, under an inch. The process repeats 20 times. At the end, you get a sheet about 1/10 of an inch thick. It comes out of the mill over 1/2 mile long, rolled into a coil weighing 10 tons. One coil makes 30,000 cans. The metal ships to the packaging plant. There they stamp blanks from the sheet, stretch the walls, form the neck. Circle complete. 60 days after hitting the trash, the can's back on the shelf. And that's how aluminum lives forever. The metal atoms in your Coke can right now might have been part of a World War II aircraft. Then became a house roof in the 50s. Then power line cables in the 80s. Then a bicycle frame in the 2000s. And now, a can in your hand. Tomorrow, they'll become part of a laptop. The day after, the skin of a spacecraft. Aluminum doesn't know aging. Each remelt returns its youth. It's the only material on the planet that can be used infinitely without degrading. Humanity produces 100 million tons of aluminum a year. 75% of all the metal ever produced is still in use today. Imagine, metal cast 100 years ago is working right now. Aluminum recycling isn't just waste processing, it's a philosophy of matter's immortality. Proof that in the right hands, the planet's resources are inexhaustible. Every can you toss isn't trash. It's a stockpile of metal for future generations. A closed loop, eternal rebirth. Aluminum will outlive civilizations and will serve those who come after us.